engineer from the China Earthquake Network Center. He got his PhD last year, and he will be visiting the institute hosted by Wei Chen during the whole year until August, I think. So here with him, and he will be talking today about using the GNSS to study earthquakes. Please go ahead.
Okay, thank you, Carlos. Hello, everyone. My name is Li Yu. Now, let's begin with my presentation. Yeah, my name is Li Yu, and I came from the China Earthquake Network Center. It also belongs to China Earthquake Administration. And I'm delighted to be here as a visitor at the Earth Observation Group. And also to be happy to share with a little bit of myself and my past work, and to share with you. And my talk's title, From Space to Ground, Using GNSS to Understand Our Dynamic. Why? Because as I know, most of you in this institute major on astrophysics, on all the subjects beyond the Earth. Well, my research subject centered on the Earth itself. So I think use this title, it's a good way to start with my visiting. And unlike many other technical presentations, my presentation is not focused on a single research progress. So it's just like an introduction of myself, my institute in homeland, and also my past primary work with the GNSS to research the Earth. So today my talk will focus on these 4 parts. The first, I will a brief introduction of myself and the institute in China. And second, I will give you a look about my research subject, the earthquake, and the tool I use, the GNSS. And third, I will give outlook of my primary research focused on two aspects. The one is the crustal deformation, and the other is the earthquake cycle deformation. And the fourth, finally, I will talk about some ideas of using the GNSS and combine with the Earth Observation Group doing to do in here. So first, yeah, that's me. Yeah, I take this picture in last month during I first came to Barcelona, and I go to this village. It's a very beautiful village. I took this picture. Yeah, I'm a senior engineer. And last year I got my PhD in the Institute of Geophysics and China Earthquake Administration. And also from 2019, I also served as a primary representative of CENC of the Earthscope consortium. And now my research interests focus on 3 parts. So first is the crustal deformation, especially in and around the Tibetan Plateau. And second, focus on the GNSS data processing, even with the high or low frequency GNSS data. And third is the earthquake, because I worked at the earthquake administration. So the third is the earthquake cycle deformation from the observing and the modeling. Yeah, let's move to my institute. The name is China Earthquake Network Center. It's short for the CENC, and it belongs to the China Earthquake Administration, and it is based in Beijing. This is our institute building, and it's far from the CENC to the ICE. It's about 9,000 kilometers. And the CENC is the national business hub, and also serves as a window for international exchange in the seismology. So CENC has 4 main functions. So one is the earthquake monitoring and forecasting, and disaster mitigating and emergency response. And also we do a lot of scientific research, and also do some of the public education and their awareness. So to fulfill these four main functions, CNC had built two networks. So the first network is the seismic networks. It which supports the earthquake early warning and earthquake rapid reporting. It consists of over 18,000 stations, which equipped with a seismometer, accelerometer, and intensimeter. And the other is the geophysical network. It concludes 6 networks. The first is the GNSS and the gravity and the geomagnetism. This network this network supports the scientific research and also the earthquake forecasting. Yeah. So after the introduction of myself and my institute, let's move to my research subject, the earthquake. So the earthquake is the sudden release of the cumulative energy within the earth. So this picture shows, imagine when we forcefully breaking a wooden stake, at first it's bent. With the increasing pressure we push, the part of the stakes will snaps, and finally it will break completely. This principle is very similar to the Earth, but the only one difference is about the Earth have occurred in the Earth inside. And the right map shows the historical strong earthquake map of the world from since the 19,000 to now. And every red dot represents an earthquake with the magnitude 7 and above. And this year for now, the largest earthquake happened in the Kamchatka Peninsula of Russia. The magnitude is 8.8, it's very big. And this earthquake also triggered a large scale tsunami. Yeah. So from this earthquake, we can see a lot of earthquake concentrate on two belt zones. So we call these two belt zones the major seismic belt. So one is the Pacific Rim seismic belt. It's like this. And the other is the Himalayan Mediterranean seismic belt from the Indonesia, India, China, Nepal, and go to the European. And in globally, every year the world will happen the 5 million earthquake, but only 15% happened on the continent. And the majority of the earthquake happened under the ocean. So that is why we feel the earthquake is very, very rare. Yeah. And for the big earthquake, like the magnitude 8 point, every year we will have 1 to 2 earthquake each year. And the 1 magnitude 8 point earthquake release the energy consists equivalent with the 1.2 thousand little boy bomb, the energy. So the big earthquake has a devastating impact on the earth and the humans. And so from this map shows the latest global seismic hazard map. With the seismologists, they use a lot of multiple data sets to compare this. And also we can see the highest seismic hazard map hazard zone also consists with the 2 major seismic belt zone. Yeah. So let's compare China and Spain. This is Spain. So we can see the Spain, the most areas of the Spain has low seismic hazard risk because of the this shows the active fault of this around the Spain, and only the southern, especially for the Galicia, around here has a little active fault. And also, this area maybe has a relative higher seismic hazard risk because of it was influenced by the northward of the African plate. But in contrast, China, almost 70% area of China has the high seismic hazard risk. Because of in China, for now we also detect a lot about 32,000 kilometers of the active fault. So you can see a lot of areas have the active fault. If here has the active fault, it has the potential to happen a big earthquake. So compared to the earthquake, I think the SPI is different. Yeah. So next to the focus, the tool I use to research the earthquake, the GNSS. So the first GNSS is the GPS, the global position system. It was initialized in 1973, and after 10 years later, this system opened to the civilian use, and now everybody knows the GPS. But why now we call it the GNSS, the Global Navigation Satellite System? Because now the GNSS has a broader meaning, and except for the GPS, it also contains the GLONASS, Galileo, and Beidou, and also other regional navigation satellite system, like in Ukraine, in Japan, and also the GIRAS in India. Yeah. For most of us, we use the GPS to know the basic purpose is to telling us where we are. So from the principle of the location by using the satellite is very simple. We just need to measure the distance from the satellite to the receiver, and use this very simple equation we can get the precise, use this distance resection method, receiver's precisely position. So due to the characters of the satellite constellation and also the signal propagation, so the GNSS has some features. The first is the high precision. We can get the precision with the centimeter or millimeter, and also it can use all weather, all time. Yeah, based on these features, the GNSS can provide the PNT service, the positioning, navigation, and timing. So its applications field has is a variety. So first is in the engineering for the surveying and mapping, and also now especially in European and America, and we use the GNSS to do a lot of precision agriculture with nobody work on it, and also use the marine navigation, aircraft navigation. But for the natural hazard, we also use the GNSS to monitoring the volcano and also the plate motion, weather forecasting, and my focus on this earthquake monitoring and the plate motion. Yeah. So now it's my primary research. The first is the crustal deformation. So we know since the Alfred Wegener composed the continuum drift theory in 1912, the worldwide scientists wanted to find a directly way to quantify the motion of the plate. With the advent of the GNSS technology, this become impossible. This become possible. The right picture shows we use the globally GNSS stations data to compute to get the horizontal velocity field of the crustal motion. So in this picture, so we can see each plate we can see the direction of we can see the direction and the magnitude of each plate movement. Yeah, and that is for the large scale research. But for the small scales, especially for country or for region, we also use the GIS to research the tectonic movement, because in order to get the detailed characteristics of the crustal deformation, especially the tectonic movement, we also after compute the GIS to get the velocity, and we use the Euler vectors to retold this velocity field into refers to a stable reference frame. So this picture shows the horizontal velocity field of crustal moment in China relative to the Eurasian plate. The vector, the Euler vector is in around here in the North European. Yeah. So from this, even once we got this result, we can see the China has the tectonic movement is influenced by two major driving forces. So one is the northeastward thrust is from the Indian plate, and the other from the Pacific plate from the westward subduction. So that's the second research subject, is the earthquake cycle deformation. So first we need to, what is the earthquake cycle? The earthquake cycle included the three main stage. So the first stage is the interseismic. Interseismic is the between two earthquakes. There are the string energy communicates very slowly. And this map shows the string energy with the time development. The right line shows the interseismic. It's just like a linear. It's very slow because the time span is very long, and the velocity is very slow. So we can just use a linear to indicate it. And after here, the energy, the crustal, the string energy accumulated in its maximum. So at here, boom, the earthquake occurred. So the string energy very slowly. So the co-seismic stage is very fast, also from the second to minutes. And this stage, the string release very quickly. And after the co-seismic, we will enter into the post-seismic. In literature, it's after the earthquake. So in this stage, the tectonic stress will adjust over the time. So this string, they also in the string line also with non-linear characters. But this period can also last for minutes to a decade. Yeah, but this picture also shows except for these three main stages, also the seismologists research told us that before the co-seismic, we also have a pre-sleep. The pre-sleep is very for now only several big earthquakes before the big earthquake we can monitoring the pre-sleep, because you can imagine if every big earthquake before the big earthquake we can monitoring the pre-sleep, the earthquake forecasting is done. Yeah, but for now the majority of the big earthquake before it we don't have seen this pre-sleep. Yeah, and also for the post-seismic, we also have the first stage of the post-seismic. We call it after sleep. It's very fast. The tectonic stress adjusts very quickly, and then they will go through the post-seismic relaxation. You use the visco relax state in this stage. Yeah, so the first interseismic. The interseismic, we often use the GNSS to got this result. This shows the China, the show before, and this is the Western American. This is relative to the Eurasian plate, and this is the relative to the North American plate. Yeah, so we can see in here, especially here, we can see clockwise. Yeah, because the India plate thrust to the East Asia plate, and in here, so from the Sichuan Basin, it's very Sichuan Basin is very hard, very hard. It cannot give these areas the deformation. So in here, the power of the stress can with the eastern Himalaya CENC cross the we can see very clearly the clockwise characters, and also for the Western America, also here we also can see very clearly clockwise, but compared to the magnitude, it's very small than here. And second, for the coseismic can tell us the which area it has the severe seismic hazard. This shows the Wenchuan earthquake happened in 2008 in China's Sichuan province. The earthquake name is Wenchuan earthquake, but the heaviest earthquake disaster happened in here. This is Wenchuan. This is the Beichuan. So the heaviest earthquake hazard happened in Beichuan. Yeah, and we can imagine if we if in 2008 we can quickly use the GNSS to got this result, so we can put a lot of rescue people to Beichuan and not Wenchuan. Yeah, and this shows the 2011 the Tohoku-Oki earthquake. The magnitude is very big, is 9 points, and also triggered a large-scale tsunami. Yeah. So in the horizontal displacement, the maximum is 5.2. It means after this earthquake, the Japan island moved east. For the big displacement is 5.2, and also with the 1.1 subsiding of the. So this also means around the coastline of the East Japan island under the sea, from the ground under the sea. And also this earthquake in China, in northeast China, we also can get the maximum about 40 millimeters displacement by this earthquake. So this earthquake strange is very, very big. So this result is the status result. We also can get the kinematic result because this we use the high frequency GS data, like the 1 Hertz or 5 or 10 Hertz data. Yeah, this shows also the Tohoku-Oki Japan earthquake. This station located in Shandong province. In here, it's about nearly over 2,000 kilometers. Over 2,000 kilometers. Yeah, this is the from the north south, and then this is the east west. We can got this map, and this also is the Shan earthquake in Myanmar. Yeah, this station is located in Yunnan province, Lantang. Yeah, it's a lot. It's about 200 kilometers near the earthquake. So why these two directions is small? Because we know this the east to west had a big amplitude, yeah, but in the north-south directions, we cannot have a clearly the waveform because of this earthquake. It was strike slip earthquake. So and the energy propagation from the west to the east. And if we can have a lot of stations with the kinematic results, so we can arrange them by the distance between the station and the epicenter. So we can get this map. We can this map. We can see the seismic energy from the near station to the far stations, like the seismic wave. And also these stations, Zhufeng, located in the Everest base camp. Also, this is from the bird view, from the sky to see the station's movement. And before the earthquake, it's here. The location is here. But during the earthquake, we had a big shaking. And after the earthquake, it's stable in here. So from here to here, it's the permanent displacement by this earthquake. Yeah. And also for the post-seismic. Post-seismic means when a big earthquake happened, after the co-seismic, the tectonic stress will adjust with the time. And this adjustment also can cause the variable displacement on the ground. So this also shows some case. This is the Nepal earthquake, and this is the 2001 the Fukushima earthquake, and it's in the center of the Tibetan, and also the Wenchuan earthquake in the Japan earthquake. This is the first 2 years after the Japan earthquake. We can see variable displacement, but after the 2013 from 2015, only here we can see variable displacement. So we can use the post-seismic deformation to because this deformation caused by under the earth is very deep. So we can use this result to research the underground media parameter, and also use this result to do some seismic risk in the future. Yeah. About the slide, we also observed the deformation. Except this, we also use the observation to do some modeling. Yeah, not just likewise, we use the surface deformation measurement, and we can build a computer model. This equation may be related to the fault and the ground observation deformation. So we can output to research the fault behavior. So first is the fault slip rate. The fault slip rate means when the faster fault slip rate indicates the higher seismic risk in the future. So we also use the interseismic velocity field to modeling to inverse the fault slip rate. The fault slip rate can also include the deep slip component, like here. It's a thrust, push another plate to move. But for the strike slip is in the parallel. It's like the deformation is not obviously under the vertical. It's very obvious in the surface. So we can get the two results, and also we can use this result to to do some critical site selection, especially for the nuclear plant. Like this. And second is the fault locking rate. Fault locking. So first, which is the fault locking? Fault locking means because we know the earthquake happened. Why here happened earthquake? Another not happened the earthquake because here has the active fault. The active fault under the tectonic stress. Because how to say the fault lock means this is the fault plane. This is the fault plane. The fault plane under the pressure is very hard, push very hard, and so if the fault is not unlocked, it will move very slowly. Yeah, very slowly. So the string energy is not accumulated in this stage. But if under the very big tectonic stress, the fault plane can lock. It's stuck. No, don't move. Don't move. In this stage, the string energy will accumulate fast. Yeah. So we can also use the interseismic to modeling along the fault plane, which area has the big index of the locking rate. It can tell us which area of the fault are strongly locked. And from here, the Himalaya. It's all the Himalaya fault have the high locking rate. And third is the fault asperity areas. The asperity means so why the is especially except for the large stress force focus on the fault plane. Another the seismologist think that there must be some big barriers and irregulations on the fault plane. So it's very smooth. It can move slowly and creeping. But if the station like this, it's easily to start. So we can also use the interseismic to inverse the fault asperity areas. And this research also happened on the subduction zone. Yeah. And for the coseismic, so after a big earthquake, we can also use the permanent displacement of the coseismic displacement to reverse the fault plane. Which area of the fault plane have the big slip? This also shows this. This is use the GNSS data and the INSIGHT data. This is also a lot of the GNSS data and the leveling, and also the triangle stations, and also use the INSIGHT data. So they can tell me the fault plane, which areas have the big slip. So after my primary research, now I'm in here as a visitor in the Institute of the Space Science. So I have some ideas of what I am supposed to do here. Yeah. So the first, I worked at the Earth observation group. The Earth observation group has the three main areas of the research. The one is the radio occultation, and the other is the GNSS reflectometry, and the third is the remote sensing using digital satellite TV signals. So the first, I think I want to use the ground-based GNSS stations to do some GNSS reflectometry. So because the in here, the GNSS reflectometry also focused on the space, use the space platform. So I want to, from the space to the ground, use the ground. So why I want to use the ground-based GNSS stations and GNSS data to do some the GNSS-R the research? Because in China, the CNC had operate a big network. Its name is the Crustal Movement Observation Network of China. It's short for the CENC. It from the 1997 to 2012, it's built around the whole China mainland about 260 GNSS reference stations, and also more than 2,000 GNSS campaign stations, and also have the gravity stations and the VLBI stations and SSR stations. In this network, we focus on the second tectonic blocks because in China we have a lot of active fault, and these active faults divided the whole China into 22 second tectonic blocks. And in China, a lot of big earthquakes happened around the second tectonic blocks. So our first is focused on the second tectonic blocks, and also the non-block boundary fault. The non-block, we have 7 non. Also, we can call the non-tectonic block, or the first tectonic block. We have 7 and the 22 second tectonic blocks. And also, we focus on some key monitoring areas, such as the Sichuan Yunnan province here, and also focus on the Tianshan mountains here, and also focus around Beijing and North Hubei. Yeah. And also, we built some neighboring countries like Laos and Myanmar. So we do a lot of projects in Laos and in Myanmar. Except the CENC, from the 2013 until to now, we also do the data sharing with other industries. This data shows the almost 2,100 GNSS container stations. Yeah, sharing with other industry. Yeah, like the China Meteorological Administration. Yeah, like that, and then also the National Oceanic Agency. Yeah. And except data sharing, we also built another 2 big projects. One is the Belt and Road Seismic Monitoring Network, which based on the CENC, they will build 230 GNSS container stations around the China. And also from the 2018, we published a big science project. Its name is the China Seismic Experimental Site, which focuses on the Sichuan Yunnan province. It's one belt zone and 5 key areas focus. In these areas, we also built 400 GNSS stations. So maybe at the end of the 2025 this year, CNC will have almost 3,000 ground-based GNSS data. Okay. So I think we can use the ground-based GNSS gamma technology to do some research. The first is monitoring the water level. From 2020 and the last 2023, the year, we used around almost 140 ground-based GNSS stations around the Yangtze River basin. So we use this data to inverse the terrestrial water resource chain, and also based on this result, we can do some terrestrial drought index like this. So this is what I want to do. And second, for the earthquake, because for now, most of the research with the TEC, the seismologists think that before and after an earthquake, especially a big earthquake, electron density disturbance may occur in the ionosphere above the epicenter. So if we can use so based on this theory, we use the ground-based GNSS data to do to inverse the TEC density. So we can get this every hour or every day. We can get the map of this, so we can see the TEC various with the different areas. But from the ground-based GNSS data, which we inverse the seismo ionospheric result, it only has the horizontal disturbance of the TEC. It only has the horizontal. And second, it's based on the based on the site location. So the result only cover the land areas, not in the ocean. And also, this is, but because we use the ground-based GNSS, it's continuous observing, so it's a high temporal resolution. But in here, the GNSS Radio Occultation, it can also do the seismo ionospheric, and also it can give the vertical distribution of the TEC, and also it's worldwide, including continent and ocean, and also, but the GNSS radio occultation, we need to weight the satellite, so it has a low time efficiency. So I think if we combine this with the ground-based GNSS, we can get the three-dimensional monitoring of the distribution of the TEC. And also we can get the worldwide and the high time efficiency seismo ionospheric. Yeah. And then this is the two ideas. And also a few days ago, talked with the Professor Tony. We have another, maybe use the VLBI to do some of the VLBI research, maybe later. So when we face the natural hazard, we cannot stop the natural hazard, but we can do to mitigate and understanding the disaster by making full and smart use of the GNSS. So I will continue with this research. Before closing, I will have a brief advertisement. Yeah, CNC has publishing an international open access journal. It's named the Earthquake Research Advance, and I also ranked Q1 scopes. And last year, the set score is 6.7. From the name, we may think this magazine will focus on the seismology, earthquake, but the EIA also wanted the GNSS and then LEO applications in earth science, and also welcome the planetary science research and development, and also the future planetary exploration plans like the hydro GNSS, like that. So we warmly welcome you submit the papers to this magazine. Yeah, that's all. Thank you. Any questions?
Yeah, I have a question. If you recommend to show the man in training based on the type of, I don't know, movement, I don't know, in case the hindsight. Yeah, there.
Yes.
Yes, I don't know what you read that is meter.
Meter.
Meter?
Yeah, meter. That's 0.1 meter. This is 0.2 meter, the 20 centimeter.
Meter. What was the initial number?
You mean
What was it?
oh, You mean how to process this rich data? Yeah, this data I use the gamma group software. Use the track model. We use another station as the reference station, and this is the mobile station. The mobile station is a reference relative to the reference station's the displacement. The reference station we also choose is in here. The reference station, yeah, the reference station is about 600 kilometers from the mobile from these stations.
Okay.
The reference station has a little impact on has a little influence by this earthquake.
Thank you.
And I have a question about the last part of the presentation with the radio occultations.
Yeah.
The ionosphere and this one here.
Yeah.
What is this disturbance in the ionosphere that happens before, after? How much time before the earthquake? Just a few minutes or a few days or?
These theories, not all the big earthquake have this thing. Only about you mean the time. For now, the research should give the answer is between the hours to days.
So,
yeah, it's very short. Yeah, so we want to, if we can detect this disturbance before the earthquake, yeah, so we can do something for the earthquake forecast. Yeah.
I'd like to comment on that same question because I read some, well, it was not science paper, but some kind of article about this, that Japan is also trying to do the same research because they observed a kind of phenomenon like that before they earthquakes as well. So
yeah,
Japan is also researching the same area.
Yeah, and also these things probably occur on the subduction zone. Yeah, a lot of these things occurred on the subduction zone. But the magazine we still don't know. Yeah.
Okay, I'm completely baffled, so I'm sorry. I am not in this field of research at all. What's the physics that explains why the electron density in the ionosphere would change for the upcoming earthquake? That is something that happens in the solid material of Earth. Can you explain me in a very simple way the physical reason for this? I don't see the connection.
Yeah, I know. Here is the epicenter. The earthquake happened deep inside the Earth, and also we can a very fast sleep. Yeah, very fast sleep. It can produce the magnetism or electricism of the Earth change, and this change can how to say can transfer from the Earth to the space. So we can use the satellite to monitoring the electricity or the magnetism. Yeah.
Good. Fine. But every time when you disrupt something electromagnetic,
yeah,
and then it's basically the electromagnetic field around itself changes.
Yeah.
And this is how you measure.
You mean how to measure the change?
Yeah, then you measure the change in the electromagnetic field. Basically, you have something electromagnetic.
Yeah. Maybe this picture maybe this picture. This maybe in very stable. The Earth is very stable, cannot change. It's very how to say, and everything has the same, almost the same pictures of the GTC distribution. But especially, but the TC distribution also caused by the solar, also by the solar and the how to say, also by the solar. But we before we calculate this map, we need to exclude the solar impact and other impact, especially we focus on the earthquake before and after. So this change is based on other days we don't have in except before and after the earthquake, the Earth is ever changing, but it cannot produce such some 就是用平常这个作为一个这个
I can try. I can try.
就是in Europe the TC is not changed very fast, but before and after the earthquake, the TC caused by the big earthquake will
time scale of the changes are much faster.
Yeah. Sorry about the
So
explanation.
what is the typical magnitude compared to a standard solar flare? Expect, and so, I mean, indeed, I mean, I guess this is very small magnitudes of this change, and so it must be buried in the global signal of the whole solar wind interaction with the Earth atmosphere and creates a lot of data. So, are you doing like some kind of special analysis to be able to extract the very short signals that you expect from this kind of effect? I mean, is it possible that this is being used for any kind of earthquake, or it's really going to be only the monster ones and specific locations? I expect also maybe specific locations will produce more of this, depending on this, because the Earth magnetic field is about, right? Okay, more or less.
Yeah, the result uncertainty is about 2 or 3 TCU. Yeah, and because now we do this research often happened after the earthquake, so we know here happened the earthquake, so we precise the data cover the time span cover the earthquake, and this TC change the almost about above 20 TCU. So compared to the uncertainty, this change is very clear.
Yeah. And now, so if you measure with radio occultations the ionosphere, what is most important to be measured? The lower part of the ionosphere, or the mid part of very high altitudes, or very rapid measurements? What is most interesting for this application?
Then the most focused on the middle. On the middle, middle.
Another question? Okay, Nuno, I don't, maybe, do you want to unmute yourself and ask the question, or should I read it? Oh, maybe.
Hello, can you hear me?
Oh, just try again.
Okay, I'm sorry, can you hear me?
Yeah.
Okay, so I wrote a question in the chat to Lee, asking if there are any machine learning models or algorithms that have shown promise in predicting seismic events or their magnitude using GNSS data. In particular, I'm more interested in data about crustal deformational measurements.
That is asking about machine learning, if there are machine learning techniques to predict, say, seismic events using GNSS data.
Machine learning. Yeah. Machine learning is a very useful technology now. Yeah, and also we use the machine learning now into in some research. One is we use the machine learning to detect the abnormals of the GNSS time series before the earthquake. Yeah, when we use the machine learning to auto detect the abnormals. Yeah, this is one. And second, we use the machine learning. Is on the it's on this. We got a lot of pictures by producing the GNS. We got the TCU distribution, and we use the machine learning to the finger also to detect the anomalies from a lot of result fingers, and also another most popular use is to use not for the GNSS. In CNC, we also use the machine learning to produce the seismic wave to detect a lot of the earthquake. Yeah, that's all.
Okay, so it's more of the analysis of all this data than predicting.
Yeah.
Okay. Thanks. Okay, so there are no any other questions in the audience. Maybe we can proceed here. It's a answers. Please wait for.